All right, Chapter 2, Part 5, Rational Functions. Root word of rational is ratio. To compare by division. We're comparing polynomials by division here. So, sum p of x over sum q of x, where both p of x and q of x are polynomials. And one constraint is q of x must never, of course, equal 0. So whatever x values or zeros of the denominator are excluded from the domain of the rational function. I think that should be pretty obvious. And then an asymptote. It's a fun word to say. And it also is fun to graph. It's a vertical or horizontal line that the graph approaches as a limit. A vertical or horizontal line the graph approaches as a limit. So it may cross a horizontal asymptote, but it will never exactly follow the line of the horizontal asymptote. And the vertical asymptotes, it may never touch. So if we look here at our two asymptotes, a vertical asymptote is an excluded x value, and it's the infinite type discontinuity we encountered in the previous chapter. Got both sets of lights on this. For some reason I don't like it. Makes it hard to see the screen, first off. Second off, when I turn around, it's right in my eyes. Okay, so a horizontal asymptote may or may not be crossed, but the graph approaches it as a limit. And here you see a couple different scenarios. In this case, it's approaching it after crossing it. In this case, it approaches it but never crosses it. So horizontal asymptotes can be crossed. Vertical asymptotes cannot, is the moral of that story. And then lastly, we have oblique asymptotes. Oblique means not horizontal or vertical. So oblique asymptotes are some line other than the horizontal or vertical that the graph approaches as a limit. So here's an example. And then if you have a shared factor of the same multiplicity in the numerator and denominator, that will manifest as a hole in the graph. A hole type discontinuity like we studied in chapter 1. You guys remembering all this? Slept since then? Remember infinite type, hole type, and jump type, which I told you you've never really run into, so don't worry about that too much. But here the infinite and the hole type will play a huge role in our analysis of rational functions. Hole would be removable. Yeah, then it's an interchangeable term, whole or removable. Even your book uses those interchangeably. It's good in math. I don't like to muddy the waters with multiple names for the same thing. But in this case, you'll encounter both so frequently, it's worth familiarizing yourself with both. As a person that studied math, I like concrete solutions, an algorithm, a single definition. The softer sciences are the ones that are big on ambiguity and uncertainty. Philosophy, for example. There is no certainty in philosophy. That always frustrated me. That was the class that broke my 4.0 in college. I ran into a professor that was not very nice. Okay, so this is your book's description of a vertical and horizontal asymptote. You don't have to write this down, but know that it exists and you may consult it if needed. So let's find a vertical and a horizontal asymptote. So first of all, the domain of f of x equals x divided by x minus 1. The first thing we need to do is sketch the graph, and that will help us Now, there are algebraic ways to find asymptotes, which I'm going to teach you. But for now, we're just going to do a little graphical analysis. That nasty problem from the homework. Okay, so around, it's kind of boring. So I can see from the graph that it has a horizontal asymptote, which from this point forward I will abbreviate as HA, lest I spend 15 minutes writing it over the course of this lesson, at y equals 1. So it has a horizontal asymptote. In other words, a horizontal line, it approaches as a limit at y equals 1. And I can tell that just by looking. You should be able to too at this point. And then a vertical asymptote, which I shall abbreviate VA from now on, at x equals positive 1. Okay, any questions about this? Just graphing it, glancing at it, and guessing where the asymptotes are. That's all we're doing here. So here's a little more challenging one. And if I look at the graph of this problem, when I put these in the old TI type calculators, you have to enclose the numerator and denominator in parentheses. Newer versions of the TI software do not require this. All right. Always got to double check my stuff because this interface is wonky. Whoa. That was spooky. Weird, man. Okay. So, what do you think here, Holden? Do you see a horizontal asymptote? You're close. And my drawing is imperfect here. It should be more like this. Maybe that'll help you. Yeah, it's at y equals 2. What do you think, Rachel? Is there a vertical asymptote that you see? No vertical asymptote. So in this case, there is no vertical asymptote to find. And it's an interesting consequence of there being no possible zeros. So 2x squared plus 1 can never equal 0. Well, that's okay because the graph of 2x squared plus 1 is like that. When is that going to hit the x-axis? Never. And so there are no zeros to create a vertical asymptote. It's kind of an interesting consequence of that denominator. Okay, so here's one for you. Graph it on your calculator, glance at the graph, and tell me what you think the horizontal and vertical asymptotes are. I'll give you just a minute. Can you tell by looking? Or you can go out to some pretty large x values if you need to. Help me remember to put my mask back up if I come in your proximity. It's difficult to hear me with it on, so I'll pull it down when I'm teaching. I'm up in the grill. Yeah. What's that mean?
How do you look at one?
Well, I would change my window. So we change it to go from negative 20 to 20. So change this x max to 20 as well. Positive. There you go. Change that. There are 4 things you need to change. So, you know, there are some fundamental errors that are worse than others. Some indicate, you know, just a deep lack of understanding of the Cartesian graph. So if you tell me a vertical line, for example, is y equals something, we got a problem. Vertical lines will always be x equals something. Horizontal lines will always be y equals something. So if you transpose these, I consider that a more grievous error than getting the number wrong, because you're misunderstanding even the directionality of the graph. Okay, so Jesse, what do you think about the vertical asymptote?
4.
X equals 4. Exactly right. Notice again, that's the 0 of the denominator, so that's the algebraic way to find it. But you should also be able to tell by looking at the graph. And then a slightly harder question. Bristol, what do you think about the horizontal asymptote? Were you able to graph this on your calculator?
Yeah.
So go to your table, and go down to a really big x value, and tell me what number you think it's getting closer and closer to. For the y value.
Well, it's just going up and down for the y.
Well, let me see.
You might still work.
Can you do what now?
You can jump to the next level.
Yeah. If you go to table set, which is second and window, and then you put in whatever you want to start at. And also your delta. Okay, so those fractions are going to be confusing. Keep going down there. It's not jumping around, it's approaching a value. Yeah. It's going to be hard to tell on yours because it's in fraction mode. Yes, ma'am. What are we talking about for the horizontal asymptote? Yeah. Not quite. Let me show you what I'm looking for here. So if you graph this, first of all, the standard window is not going to show you very much. So if you didn't manipulate the window, you didn't get the full picture of the graph. So here's the standard window, and it just shows a portion of it. But if I change my window to go from negative 20 to 20 on both the x and the y, notice it's 4 things I'm changing here. It gives me a more complete picture. So clearly I'm approaching some horizontal value here, but it's not doing so very quickly. So let's go up to 0 on the graph, and I'll go up by 100 each time, I'm sorry, on the table. And so what value does it look like I'm approaching here?
0.
And look carefully. Can you see this number? It's getting closer and closer to 5. So the answer is a horizontal asymptote at y equals 5. Again, if you just looked at the values graphed by the standard window, that wouldn't have been obvious. You have to think about, as you get closer and closer to infinity, what is y value is going to be. It doesn't have to go to a constant, but it often will. And the way you find it is just use really high values of x. If you're just doing a graphical analysis. Okay, so ways to graph them. These are the algebraic ways to find the vertical and horizontal asymptotes. I'll just give you my take on it. So first of all, vertical asymptotes may occur, I don't use shorthand. Excuse me. At zeros of the denominator. So I need to check the zeros of the denominator for vertical asymptote behavior. So it's going to be one of two things. If you have a 0 in the denominator, it will be a vertical asymptote or it will be a hole. So if the 0 is shared, with the numerator, then it is a hole and not a VA. So if the 0 is shared with the numerator, it's a hole, not a vertical asymptote. Otherwise, it's a vertical asymptote. Now, horizontal asymptotes are a little more complicated. You got 3 scenarios. First of all, you need to identify the degree of the numerator. We'll just call it n. Then you need to find the degree of the denominator. And we'll just call that m. Just picking them at random. Could be a and b, x and y, just variables. They're going to stand in for the degree of the numerator and the degree of the denominator. So our 3 scenarios are as follows. N is greater than m. So that means the degree of the numerator is higher. Are you with me? If n is greater than m, there is no horizontal asymptotes. If n equals m, if they are the same degree, then it has a horizontal asymptote at the ratio of leading coefficients. And if I had, so we'll just say we've got some rational function here, and you'll have some leading term in the top and some leading term in the bottom. Whatever this number is that's attached to our highest power of x in the numerator, divided by whatever this number is, what is attached to the highest power of x in the denominator. So y equals a sub n over a sub m is our horizontal asymptote. That's the most complicated scenario when they have the same degree. As far as finding the horizontal asymptote goes. All right, so Question, Rachel?
So at f of x, we put a and x, and is that plus what?
Plus whatever.
Just whatever.
This is just the leading term. I'm trying to be general here. This isn't a specific function. It's meant to stand in for any possible function. So a sub n times x to the n just means whatever the highest term is of the numerator's polynomial. And a sub m x to the m is whatever the highest degree of, or highest power of x is in the denominator's polynomial. So we take the ratio of those two coefficients. The ratio of the leading coefficients. And then the final scenario here is when n is less than m. In other words, the degree of the denominator is higher. And in this case, you've got a horizontal asymptote at y equals 0. So vertical asymptotes may occur at the zeros of the denominator. I need to check that to see if it is a shared zero with the numerator. If it's a shared zero with the numerator, it's a whole instead of a asymptote. And then for the horizontal asymptote, I need to analyze the degree of the numerator, degree of the denominator, and based on the relationship between those two values, I'll pick one of these three categories for finding the horizontal asymptote. Questions about that? All right, let's put it to practice. So here's a rational function, and I notice the numerator is degree 0. If there is no power of x visible, then it is a 0 degree polynomial. So the numerator here is degree 0. The denominator is degree 1. So our horizontal asymptote situation is n is less than m. So it has a horizontal asymptote at y equals 0. You'll remember that from the previous, the last one we talked about. So when the numerator degree is less than the denominator degree, horizontal asymptotes at y equals 0. Now let's talk about vertical asymptotes. Well, the 0 at the bottom is at x equals -5. That is not shared with the numerator. The numerator, in fact, has no zeros at all. And so I will say this is a vertical asymptote at x equals -5. So let's sketch the graph here. All right, so I know it's going to approach the x-axis. In other words, where y equals 0 as a horizontal asymptote. And I know it's going to have a vertical asymptote here at x equals -5. So once I know those things, 7 over x plus 5, we'll see its behavior between the asymptotes best by graphing it. Oh yeah. So under and over. You gotta ride that asymptote when you graph. But don't touch. Okay, any questions about this one? All right, in that case, let's go on. So, degree of the numerator. What is it, Bristol? Highest power of x in the numerator is polynomial. So what power of x is this? And there are no other powers of x listed, so it is the highest. So what is the degree of the numerator? Very good. So the degree of the numerator is 1. What about the denominator here, Grace? Well, not in this case. What's the exponent here? So that's the highest power of x, meaning the degree is what? Very good. Okay, so we have a scenario here where n is less than m, same as last time. So we have a horizontal asymptote at y equals 0. And now let's see if we have any shared zeros or anything weird going on. So I'm going to factorize, before I do my vertical asymptote analysis, I'm going to factorize that denominator just so I can make sure, remember the difference of squares factoring trick. I see there are 2 zeros in the denominator, and they are at x equals 2 and x equals -2. Both those values will make the denominator 0. Neither of these are shared with the numerator, and so they are both vertical asymptotes. So I have a horizontal asymptote at y equals 0, 2 vertical asymptotes at x equals 2 and x equals -2.
We were just writing vertical asymptote.
You could, yeah. That's not the way your textbook would write it now, but it's not wrong. It's a little unconventional. Okay, so first of all, x equals -2 and x equals +2. There's our vertical. And then our horizontal is at y equals 0, which is also the x-axis. Now to see its behavior around those asymptotes, we need to use our calculator. It's the best. You could find a few points, but this is more efficient by a large margin. And I'm still zoomed way out, so let's go from -5 to 5 like I did here. Okay, so that gives me what I need. So it's going to be under here, cut across here, and then over on that side. Like so. As always, stop me if you have a question, thought, comment. Otherwise, I will assume you've got this down cold. Okay, let's move on. So here you would find 2 vertical asymptotes and a horizontal asymptote at y equals 0. The vertical asymptotes would occur at the zeros of the denominator, which are at -4 and +3. We won't spend any more time on this because I think you've seen enough of these. All right. So let's do this one. We have a different scenario here. Jesse, what's the degree of the numerator? Good. And then Rachel, what about the denominator?
6.
6 is the constant term. With degree analysis, we're looking for the highest power of x. So what's the highest power of x you see? Just one. So this is the case where n equals n. And we've got a horizontal asymptote at the ratio of our leading coefficients, the coefficient part of the highest degree term in both the top, which is 2, and the bottom, such as 1x, meaning it's just 1. So I can rewrite that as just y equals 2. Horizontal asymptote at y equals 2. And then the 0 for the bottom is going to be a vertical asymptote because it's not shared. I don't need to factor it because it's just one linear factor. So x minus 6 equals 0 means x equals 6. So vertical asymptote and horizontal asymptote. And then they say also find the intercepts. So you could do that again, finding points to make your graph more accurate. And intercepts are fairly easy points to find. So we'll do that. That's a different argument than finding the asymptotes. So finding the intercepts, if I want the x-intercept, that's where y equals 0. And do you see if I have a fraction, some a over some b? In order for that fraction to be 0, the numerator has to be 0. You guys see that? So that's the only way a fraction can be 0 is if its numerator is 0. So we will set the numerator equal to 0 to find our x-intercept. So subtract 5 and x equals negative 5 over 2. And for the y-intercept, x equals 0. So you just find f of 0. So that's 2 times 0 plus 5 over 0 minus 6. And so that's negative 5 over 6. So those are my intercepts. They can help make your graph a little more accurate, is the purpose there. So we've got all the information we need to make a really good graph here. There we go. So first of all, let me draw in the asymptotes. X equals positive 6. Be something like that. And then y equals 2. See, it's there. Would be something like that. And then plotting the intercepts, x equals negative 5 over 2. So that's about here. And then for y, it is negative 5, 6, which is just less than 1. So it should be something like that. Now let's use our calculator to finish our graph. 2x plus 5. And you might say, well, why didn't you just do that in the first place and dispense with all this? Well, the graph wouldn't have been as accurate without this additional work. Let me zoom standard here. Yeah, okay. Ride the asymptote. Like so. Stop me if you have a question. Everybody cool on this? All right. Oblique asymptotes. So oblique asymptotes are when the degree of the numerator is higher than the degree of the denominator. You remember I told you when n was greater than m, there is no horizontal asymptote. You guys remember this? That's because instead you have an oblique asymptote that can only be found through polynomial division. Don't worry about the details here. I will, as usual, demonstrate this in an example. Oblique asymptotes. Another fun word to say. The section of your abdominal muscles that's particularly hard to channel. You need to do something exotic like a rollout or a Saxon side bend, like I saw Holden doing yesterday. All right, graphing a rational function. So here we have x squared plus x minus 8 divided by x plus 3. We're going to determine asymptotes and intercepts and then graph and state its domain. Notice here, we've got that scenario that they predicted. Ian, what's the degree of the numerator here? Look carefully. And then what about the denominator, Holden? Good. So our scenario is n is greater than m, and that means we'll have an oblique asymptote.
Does that always mean it'll have one?
Indeed, yeah. If the degree of the numerator is higher, yes, it will always have an oblique asymptote. And the oblique asymptote, the shape will be determined by the difference in degree. If the difference is 1, like it is here, it will be a linear oblique asymptote. If the difference is 2, it'll be a quadratic oblique asymptote. Don't worry too much about that. Just find it and sketch it. All right, so what we need to do is polynomial division to find the quotient. You remember this from our previous section. So here, special number, list of coefficients. What's our special number in this case? Who can tell me? Very good. The additive inverse of whatever modifies the divisor. So in this case, plus 3 is the divisor's modifier, so minus 3 is our special number. 1 minus 3 minus 2 is positive 6, and so negative 2. When we are finding the oblique asymptote, we don't give a hoot about the remainder. Don't even care. All we care about are the coefficients of the quotient, because that quotient is our oblique asymptote without the remainder. So cast the remainder away. In order to find the oblique asymptote, you perform the division. And then you use that to write the quotient polynomial, and that is your oblique asymptote, x minus 2. Now, there's no horizontal asymptote here, so we don't have to worry about that, but there still is the potential for a vertical asymptote, and we will see that one exists. If we factorize the numerator, that's going to be x, well, actually, that doesn't factor. It's an irrational solution set, so I needn't worry about it having a shared 0. So, but as far as a vertical asymptote goes, it's at x plus 3 equals 0, which means x equals negative 3. So I've got an oblique asymptote and a vertical asymptote. And then as far as the intercepts go, well, if I set my numerator equal to 0, that will be my x-intercept. Remember, that's where y equals 0. So that's going to be where 0 equals x squared plus x minus 8. The way to solve this is the quadratic formula is your best way. So x equals, here we have a equals 1, b equals 1, c equals negative 8. So x equals negative b plus or minus the square root of b squared minus 4ac over 2a. To be the litmus test for every good high school level mathematician. Did you have this mess memorized? Nowadays, nobody memorizes anything. I don't know if that's good for us. A skill that will be forever lost. When I was your age, I had to memorize every phone number for every person I knew. Can you imagine? But we did it. So this is b squared, that's 1 squared or 1, minus 4ac. So that's minus 4 times 1, which is 4, times negative 8. So that's negative 32 over 2 times 1, which is 2.
Positive 32 since it's negative 4 times.
It will become positive.
Oh, okay.
Yeah, I'm going to do that on the next step. You're one step ahead of me. No, it's okay. You were right, but you are one step ahead. All right, so negative 1 plus or minus the square root of positive 33 over 2. So these are our two x-intercepts. We're going to estimate those with a decimal here. So negative 1 plus the square root of 33, and then divided by 2. So that's about 2.4. And then negative 1 minus the square root of 33, and then divided by 2. It's about negative 3.4. Just as an estimate. So that gives us our intercept, our x-intercept. Our y-intercept is going to occur where x equals 0. So we just have to find f of 0. That's going to be 0 squared plus 0 minus 8 over 0 plus 3. So that's going to equal negative 8/3. And if I approximate that with a decimal as well, it's about negative 2.7. So that's going to be at y equals negative 2.7. All right, so now we've got all the information we need to graph this. Let me consolidate. Okay, so there's all the stuff we need. And now let's use it to sketch a graph. All right, so oblique asymptote at x equals negative 2. You see how that's going to be a diagonal line through negative 2, like so? If I have to refresh your memory about how to graph linear equations, I will. But remember, it's mx plus b, where b is the y-intercept. So negative 2 is the y-intercept. The slope is 1. So hopefully you see how it would look like this. All right, and then vertical asymptote at x equals negative 3. That's going to be something like this. And then the y and x intercepts, let's plot those. I'll use green here. So about positive 2.4, which that'd be I'm not sure which side of that. Oh, that'd be on this side. Yeah. And then negative 3.4. Yeah, just past this. And then negative 2.7 on the y, like so. So I can kind of tell that this is going to be actually that should get closer to the asymptote. So it should be this. But we'll check it with the calculator and make sure my guess is correct here. X squared plus x minus 8 divided by x plus 3. Yep. Okay. Questions about any of this? Asymptotes. Super fun. Visuals are satisfying to me. I don't know. It's really make me happy. Okay, so we have to beware of a certain potential scenario. That's when we have a shared factor in the numerator and denominator. That will not manifest as a vertical asymptote. It will instead manifest as a whole. So here's a scenario where we have a whole. If I factor both of these quadratics, and I'm doing the factorization as an afterthought, but for some of you that may not be in your skill set. If so, you need to refresh your memory on that. There's tons of material out there, or you can ask me and I'll help remediate you. But we're using a factorization shortcut here, and that is the difference of squares shortcut, which tells me that's x plus 3 times x minus 3. And down here, I need two numbers that add up to -1, multiply together to make -6. That's going to be x minus 3 and x plus 2. So I see there is a shared 0, meaning we have not a vertical asymptote, but a whole at x minus 3 equals 0. Why my ampersand came out so weird there. There we go. Which means that x equals 3. So we have a whole at x equals 3, and then a vertical asymptote at x equals -2. We've got a horizontal asymptote, because we have n equals m here, at the ratio of the leading coefficients, which is 1/1 or just 1. And we won't worry about the intercepts in this case. Hey, Brian, welcome back.
Glad to be back again. I was walking around saying hi.
Our noble leader returns, ladies and gentlemen.
I hope you got bigger leaders than me. That looks like Greek right there.
Well, these guys are probably thinking the same thing. They just don't want to tell
That looks like something they found on one of those ships in Roswell.
you.
Y'all get that reference?
Okay,
It was on Big Bang Theory. I'm
Yeah,
talking the joke from Big Bang Theory.
An important bit of history to note. There was a book by a 5-star general that was the administrator of the Air Force Base during the Roswell incident. It's worth a read. It'll make you wonder. Okay, so let's sketch our graph. And again, we'll dispense with the intercepts because that'll be obvious once we plug this in the calculator. So a horizontal asymptote at y equals 1, something like that. A whole at x equals 3. We'll get back to that. Vertical asymptote at x equals -2. So the whole is going to come in when we draw the graph itself. So we're going to do x squared minus 9 divided by x squared minus x minus 6. All right, pretty straightforward. I'm going to ride the asymptote like so. And then ride the asymptote till it gets to 3. Then we got to actually, there we go. So you see how the hole manifests in the graph. And if I graph this on the calculator, that hole will not be obvious. In fact, it will look just like the graph continues right through that point, unless you zoom way in. So this would be very easy to miss. And as I usually do, warning you, this is an often missed test question. People overlook the hole, or they call it an asymptote or whatever. So important to add this to your points of additional study. Okay, so solving a rational equation. This is where we've been going with all this. Solving a rational equation. So the initial step here is going to be to combine all terms on the left into a single rational expression. So to combine fractions, we need a common thing. What is that thing? Indeed, we need a common denominator. So the way we're going to make that happen is I'm going to rewrite x as x over 1, and then I'm going to multiply top and bottom by the denominator over here. So I have x squared minus 6x over x minus 6 minus 4 over x minus 6. Now you see I have that common denominator. And so because a over c minus b over c equals a minus b over c, we can combine fractions in this way. So I'm going to use this to rewrite that left side into x squared minus 6x minus 4 over x minus 6 equals 0. So let's see here. Let's shrink all this down. It's getting a little unwieldy. Okay, there we go. So that means the numerator is equal to 0. Is going to solve this, but I have to make sure to not violate the division by 0 rule. So I'm going to say x could never equal 6, and that's, again, because of that denominator. So if I set the numerator equal to 0, that will give me the x values that solve this, but I have to be careful never to divide by 0. So 6 is disallowed. If we happen upon 6 as an answer, it's no good. All right, so I want to use completing the square here, because this is a problem that just cries out for it. So I'll rearrange it into this format by adding 4 to each side, and then making room to complete the square on the left and balance the equation on the right. In order to complete the square, I take 1/2 of the linear term, and I square it, and then I'll add that to both sides. That creates a perfect square trinomial, a squared minus 2ab plus b squared. So I can factor that into a minus b squared. Like so. And then using the square root property, neither of these answers are 6, and so they're both valid. 3 plus or minus the square root of 13. Let's test this. So I'm going to graph x minus 4 divided by x minus 6. And so it should have zeros at this point if we did our job right. So first of all, let's do 3, trace first. 3 minus the square root of 13. Sure enough, that looks like a 0 to me. And then let's do 3 plus the square root of 13. Again, looks like a 0 to me. So you see how that's graphical confirmation of our algebraic work here. You can use the calculator to confirm. Don't use it to substitute for this, because this is important practice. And the only way you'll understand. Okay, any questions about anything we have discussed? Or thoughts or comments? In that case, I would like for you to complete page 138, 210, 20, 32, and 58 by Monday.